Okay, so my talk is in fact composed of two parts. The first part is on tandem duplications, and second part is on segmental duplication and deletions based on copy number profiles. So naturally, I will present them separately. So each about maybe 25 minutes. So you can pause in the middle. So which make probably would make your life a little bit easier. Um, Tandem duplication is actually a very simple operation. So basically, you are given a string, and you pick a substring x, and copy x once to have xx. So xx is typically called a square. So this tandem duplication themselves. First, started in copying systems as early as in 1984 by Uhlenfuch and Rosenberg. In biology, in this famous paper by Sostek and Wu, they pointed out that gene duplication is the main driving force behind evolution, and the majority of duplication affecting organisms are tandem duplications. So, as a matter of fact, in the first human genome, after it is sequenced, it was found that about 3% of the data are in fact in the form of tandem repeats. So, as another example, McDonough, et al. Showed in 1993 that the Huntington disease is actually related to the tandem duplication of three nucleotides, CAG. So related to tandem duplication, we have two fundamental questions. The first is what I call the decision problem. So basically, I give you S and T. S is a source, T is a target. Over some alpha, beta, sigma. The question is, can T be obtained from S using tandem duplications? The second is more of the optimization version. So assuming T can be obtained from S using tandem duplications, can you compute in the minimum number of tandem duplications to convert S to T? Okay, so this is called optimization version. So for the decision version, in fact, this was first studied by Su in 1906. He showed that for binary alphabet 0, 1, any T can be generated with one of the six square free string, and each of them is square free. So for example, T is 0, 1, 1, 0, 0, 1, 0. Since between the start and end, which are both 0, we have ones, right? So I would pick the fifth string in the set. So 0, 1, 0. I first copy 1, 0 to 1, 0, 1, 0, right? And then in the second one, I copy this red 1 to get two consecutive ones. And lastly, I copy this red 0 to have two consecutive zeros and to have T. Okay. On the other hand, if sigma is of size at least 3, then this square free ancestor set is infinite. And moreover, it is possible that from S you cannot generate T using tandem duplications. And here is an example. S is 1, 2, 3. T is 1, 2, 3, 2, 1, 2, 3. So I will leave this as a quick question, for you to think why S cannot generate T using tandem duplication. Overall, whether this question, this decision question, can be answered in polynomial time for sigma at least of size 3 is still open. On the other hand, for sigma equal to 2 or 0, 1, a lot has been done. I will not go over all the references listed in the proceeding. For the second optimization question, first of all, this minimum number is called TD distance between S and T. If we convert this question to a decision question, basically you want to know whether the tandem duplication distance between S and T is at the most k, and then we could also use KTD distance to represent this number. So computing this number, the minimum tandem duplication distance was first posed as an open question in 2004 by Rupert et al. So in other words, whether we can compute this number in polynomial time or the computation is NP hard. Okay. For binary alphabet, Noga alone et al. Showed that the maximum TD distance between a square-free string S and the target string T, where T is of length n, is theta n. This does not really answer the previous question, but it is sort of related. Okay. So last year, Manuel Lafond, myself, and my student Peng Zhou showed that this problem is actually NP hard for an unbounded alphabet. This was posted on archive last year and presented at the Stacks this year. So this solves the 15-year-old open problem. And for finite sized well alphabet, Cyclis and Pilati posted about 2 months ago that for sigma of size 3, 4, 5, they claimed that they could modify our proof to have the NP completeness, NP hardness result. Okay. For the remaining sigmas, for example, sigma is binary. The problem is still open. So let me quickly go over the idea. So first of all, in our proof, instead of converting S to T using tandem duplications, we consider the other way. So we consider contracting T back to S. So a contraction is symmetric to tandem duplication, right? So you take XX in a string and delete one copy of X to have AX. Okay. Moreover, in our proof, we consider S to be a permutation. So in other words, we only consider a special case of the K TD distance problem, and this version of the problem is called example TD. So basically, in the next maybe 10 minutes, I will try to show the example TD is NP hard for an unbounded alphabet. Okay. So first of all, before giving some of the details, let's look at the difficulties. So we have two difficulties. So the first is we need a suitable problem to reduce from. And the second one is the sequences that we designed should form a promised version. So in other words, it is always possible to construct T from S. Moreover, the number of contractions, optimal number of contractions, should be related to the problem that we are reducing from. Okay. So for the first one, we define a new problem called cost effective subgraph. Okay. As you will see in a minute, so I will give enough details for this one to give you some feeling about the reduction. For the second one, we need to force this when we reduce the CES to tandem exemplar tandem TD, we should force the contractions to behave in our way. Before anything or any detail is given, you can see in general the contractions could be pretty ad hoc, right? So I select a segment and duplicate it, right? For the next one, the next substring could overlap with the one that has just been duplicated, right? So this is basically the generic idea. So now some details. The first one is about this cost-effective subgraph problem. Given a simple unweighted undirected graph G which is VE. For a subset X of V, I define EX as all the edges such that their vertices are both in X. So in other words, the EX is the set of edges inside this set X. The cost of X is a little bit tricky. So C is some positive integer. So it's a C times EG minus EX. So in other words, these are the number of edges that are not in EX. Okay, plus X times the size of EX. So intuitively, so basically for all the edges not in EX, we give it a weight C. For any edge in EX, we give it a weight size of X. Okay. So the cost-effective subgraph problem is simply to find a subset X of minimum cost. Here is a very simple example illustrating this problem. So here we have UVWXY, a graph with 5 vertices and 6 edges. Suppose C is 4, and if we select X as UVW, okay, this triangle, the cost of X would be 4 times 6 minus 3. So those are 3 edges, plus 3, which is the size of X, times the 3 edges, UV, VW, UW, so giving us a weight of 21. Okay. And if we instead select this 4 vertices, VW XY, the weight would be 24. On the other hand, if we select any single edge, let's say VW, the cost would be 22. For the problem, since we want the X with a minimum cost, so this is what we want, right? So this gives you in fact some basic ideas about showing the CES problem to be NP-hard. So in fact, we just reduce clique to CES. So R equals C times M. M is the number of edges in G. C and P are parameters. We set C as 3k/2 and P as k/2 times k choose 2. So GK, we showed that in the GK is yes instance for clique. So in other words, G has a clique of size K. If and only if G contains a subset X of cost R, which is 3K over 2 times M minus this P, right? So I will not give more details because it mostly involves some calculations. Okay. So now let's look at the reduction. So since the reduction is very long, it's very, in fact pretty tedious with all the details. So I will just illustrate the most important ideas. So here we reduce CES, the cost-effective subgraph problem, to example TD. Given the input for CES, which is the graph G, that's a parameter C and R. R is the cost, C is the weight of for the edges not in X that you want to set. And we let VG be V1, V2, Vn, and the size of E is M. For each VI, we associated it with a distinct character Xi. So initially, the idea is that S, which must be a permutation, right, is roughly X1, X2, and Xn. And S prime is to simply duplicate each of Xi. So X11, X2, X2, Xn, Xn. Okay. So T is constructed as S prime, E1, E2, EM. So each EI is a substring corresponding to the edge EI. And of course, all those EIs must be removed to construct T to obtain S. The goal is that some doubled Xi's of S prime will be constructed to have S double prime, and this correspond to the vertices of cost effective subgraph. With respect to the previous example, suppose we want construct T doubled Xi's, and this correspond to the T vertices of the corresponding C cost effective subgraph. If in the previous example, if UVW XY correspond to X1, X2, X3, X4, X5, we would have T equal to 3. In other words, you would construct the two X1s and two X2s, two X3s, and you leave the X4, X5s alone. Okay. So after T is contracted to S double prime, followed with the capital EIs, E1 to EM, we force each EI to always use S double prime to sequentially construct to S. Okay, so in other words, so sequentially we construct S double prime, EI plus 1 all the way to EM to S double prime, EI plus 1, etc. So in other words, this EI would be eliminated. But in this case, we want to have two options when we eliminate this capital EI. So if EI little EI is VJVK, and we have chosen to contract xj and xk to S double prime. In this case, we could contract EI this way using T moves, T contractions. If either xj or xk is not selected to be contracted previously, then we would have to contract ei using a C move, and the total cost to eliminate EIs would be C times M minus E plus TE. I mean, loosely speaking, this is a way to balance, do some kind of balancing to reduce, the total cost. And this is exactly related to the meaning of, CES. Okay. Here, this little e is the number of edges contracted using the first option. So in other words, um, both endpoints of those edges were chosen to be contracted to have S double prime. So to enforce everything is done according to our plan because the duplication and in this case contraction is very flexible. We actually need to make this idea in the previous slides solid by doing something extra. So in other words, for each little xi, we actually augmented it with string capital xi, and each ek is constructed using this repeated xi. So for instance, if edge ek is vi vj, and the corresponding ek will contain, well, a part of it will contain xd x all the way to xi minus 1 d. Then at the xi, so I leave the exponent to 1, and then xi plus 1d, x j minus 1d, and again x j. So the exponent I will leave it at 1. The remaining ones, they all have exponent in it. So the details of the formal arguments will be could be found in or archive paper or in the stacks paper. So the summary of results, well, first of all, the example TD problem is shown to be NP complete. The example TD problem is also shown to be fixed parameter tractable. I will not go over the details, but I list very simple properties here to help you. Maybe if you want to read more of that paper. So open problems. First one is the general KTD distance problem FPT. In other words, if S is not a permutation, can we still show that the problem to be fixed parameter tractable? Okay. The second one is for binary alphabet is the exemplary TD problem still NP hard. Okay. Last one, this is on the decision question that I already asked a little bit earlier. So for sigma of size at least 3 is the problem of deciding whether S can be converted to T using tandem duplications. I don't care what is the number of this duplications NP hard. So these are the three outstanding open problems. So I will. So for well, some of you, if you want to take a break, you should pause. And since I'm going to cover the second part and next, they are related, but not completely kind of identical. Okay. So you could take a little break to go over my second part. Okay, so now let's look at the second part, which is segmental duplications and deletions involving copy number profiles. And this is based on our CPM paper, this year. So first of all, for the background, we'll try to spend a little bit of time to go over the background. So in cancer genomics, central problem is to investigate the inter-tumor genetic heterogeneity, which is important to cancer prognostics and the explain of drug resistance. For some cancers, like this one, the high grade serous ovarian cancer. So this is mainly reflected in rearrangements and large number of duplications, and certainly some deletions. So because of that, in the later stage of this kind of cancer, the genome changes significantly. So therefore, to do the sequencing is not that meaningful anymore. So in this case, the data are mostly represented as copy number profiles, CNPs for short. So what is copy number profile? Well, so let G be a genome over an ordered set of n segments, and ordered set of n segments, G1, G2, Gn. The copy number profile of G is basically an n vector, C1, C2, to Cn, such that Ci is the number of segments of Gi in G. Okay. An example is like in this case, G is composed of let's say 8 segments, A, B, C, D, E, A, D, E. The corresponding CNP would be 2, 1, 1, 2, 2. So this 2 means I have 2 copies of A. This 1 means I have 1 copy of B, etc. So in general, at this point, algorithms are still needed to process, the CNP data. The area is, widely open, and lots of, open problems. We, started the research, due to, the following paper by Shamir et al. At the CPM, 4 years ago. Okay, they call this problem copy number transformation problem. So we are given 2 copy number profiles, C1 and C2, and the problem is to use the minimum number of block duplications and deletions to transfer C1 into C2. So here, the duplications and deletions are performed or applied on the CNPs directly. So formally, copy duplication on a segment means increasing the value by 1 on every element in that segment. So in this case, let's say C1 is 1, 2, 2, 1, 2, 1, right? So I want in the duplication of the segment 2, 2, 1, 2, 2, 2, 1, 2. So by this definition, I will just increase the value of each of these 4 elements by 1. 2 becomes 3, 2 becomes 3, 1 becomes 2, 2 becomes 3. Okay. A deletion is exactly the other way around. So you select a segment and you decrease the value of everyone except zeros by 1. Okay, so remember that if in the duplication, if one item is 0, then you cannot increase it to 1. And similarly, if over here, if you already have a value, for example, 0. If you suppose choose the same segment to do one more duplication, this 0 will stay as 0. So because CNPs cannot contain negative values. This is example that you use 2 duplications and 1 deletion to convert C1 into C2. I will not go over the details. You can pause and verify by yourself. So linear time algorithm using dynamic programming was given by Shamir et al. Solving the problem completely. But on the other hand, we noticed that this model has a problem when the evolution depth is large. And here is a very simple example. Okay, so on the right I have CNPs. On the left I have the genome or sequence, right? So when I duplicate BCDE, so you would increase the corresponding value at BCDE by 1, right? It becomes 1, 2, 2, 2, 2, 1. Okay. So then next, if I duplicate a DEB again, so suppose here everything is tandem duplication, right? So DEB, DEB. So you would increase the value for B to 3, and D and E also to 3, but you did not change the value of 2. So in other words, if you go directly from CNP to CNP for this, 2, you cannot, do it with 1 duplication, right? But on the string, now you can do it. Okay, so there's, some kind of a discrepancy, okay, over here. Okay. So in general, we can see, the duplication and deletion on genomes can lead, to non-contiguous changes of values on the corresponding CNP. Okay. Anyway, so in general, algorithms are lacking for this kind of problem. You will see this a little bit later when I talk about the new problem. So in this part, basically we investigate 2 fundamental problems. The first one is called MCNG, which was first appeared in ACM-BCB 2018. In this one, we studied the following problem. Given a genome G and a copy number profile C, use a minimum number of duplications and deletions on G to generate another genome G prime, such that the CNP of G prime is equal to C. So in this case, we are not performing anything directly on the copy number profile, right? So in other words, we are not dealing with numbers. Instead, we are still doing those duplication and deletions on a sequence or genomes. And the problem is realistic and seems to be very hard. For the generic version, no theoretical result was known. So Chinga, considered the special case when the duplication must be tandem. For that case, we showed that the problem then be hard. Okay, and a generic greedy-based algorithm was also proposed and implemented. So in this work, we show that the problem actually does not admit a constant effect approximation unless P is equal to NP. Also, the problem is W1 hard, parameterized by the solution size, the number of duplication and deletions to convert G to G prime. The second problem is new. So in this one, which we call the copy number profile conforming. is defined as follows. Given two copy number profiles, C1 and C2, compute two strings S1 and S2 with CNP of S1 being C1, CNP of S2 equal to C2, such that some distance between S1 and S2 is minimized. Okay, so we show that if the distance is the string breakpoint distance, then this problem is actually polynomially solvable. Before going into the details, let me, for completeness, let me give the definition of segmental duplication deletion. In the duplication case, you basically select a segment AI all the way to AJ, and put this segment before some AK, where K is less than or equal to I, or after some AK, where K is greater than or equal to J. If either K is equal to I or J, so then the duplication is exactly tandem, right? So here is an example. You have 1, 2, 3 ABC. I will try to duplicate this segment, 3AB, and I basically put this segment at the end of C, 3AB, right? And in the case of tandem duplication, right, 1, 2, 3, right? So if I want a duplicate 2, 3, so in this case, I will just put this 2, 3 at the end of 3. So I have 2, 3, 2, 3. So the second one is tandem. Okay. So deletion is even more straightforward. You just select a segment and delete it, right? So like in this case, if I want to delete 3AB, the resulting sequence would be 1, 2, 3. Here is the two example, the example showing this how this MCNG works, right? So you have G, which is AB, AB, CD, CNP of G is 2, 2, 1, 1, and the target copy number profile is 3, 3, 1, 2, and you can copy AB, then D, both tandem, to have the sequence AB, 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 C, D, D, which has the corresponding copy number in the profile. So I will I have a couple of slides over here for showing that MCNG is hard to approximate, but since I'm not going to have enough time, so I will just quickly go over the general ideas. Okay. So in this case, we reduce T set cover to MCNG. So T set cover is a special case of set cover where every set contains at most T elements. While set cover is well known. Well, T set cover is maybe relatively speaking less known. Nonetheless, Luca Trevisan showed about 20 years ago that T set cover cannot be approximated within a factor of log T minus C log T. Here T is a constant. Unless P equal to NP. Okay. Finally, a solution for set cover is an exact cover if the sets in the solution are all disjoint. Okay. So all reduction. So basically, can be generalized to this problem. This generic problem or minimization problem B has the property. So first of all, any exact cover of S of size K, where S is an instance of T set cover, can be transformed into a solution of size K for DS, which is the converted instance for problem B. In this case, M, C, and G, and any solution of size K for GS. In this case, an instance for M, C, and G can be transformed back to have a solution for S, or the T set cover. Okay. So the reduction is very simple. So the rough idea is that because T is a constant, right? So T is a constant. We just need to select T large enough. So T is constant, so I can enumerate all subsets of size at the most T. So in other words, you could have 2 to the T of them, right? And after in the transformed kind of larger kind of instance, right? Apparently, if originally you have a solution of size K for T set cover, you must have a size K exact cover. Okay, and so I will not go over those details. So basically, we can show that the S has a set cover of size K if and only if B, in this case M, C, and D, has a solution of size K. So therefore, any factor B approximation for B would provide a factor B approximation for T set cover with T less than log T minus C log T by assumption. So then we have a contradiction to Trevisan's in a negative result. Okay. So here, we actually just showed the corresponding detailed construction with some example. Because my time is running out, so maybe I will skip this part. So basically, you construct a genome G based on the input of T set cover with some sets. And you set a CNP of each of this yellow symbols as 1, and the CNP of the remaining elements as the number of sets containing UI minus 1, right? And so with respect to this example, so this would be your corresponding genome. And the solution would be certainly, well, one exact cover, right? 1, 2, 3, 4, 5, 6, A, B, C, D, E, F. So I will skip the remaining ones. So in fact, here we only show the case for deletion only. Okay, when duplications are also allowed, we also need to show that this solution is kind of optimal. But on the other hand, I'm not going to have enough time to talk about this. I will skip this part. So this is the conclusion in approximability conclusion. For the second negative result that MCNG is W1 hot. We just use very much in the previous reduction. Lastly, I have about maybe 10 minutes to go over this copy number profile conforming problem. So in this case, we are given 2 CNPs, C1 and C2. You want to compute two strings S1, S2, such that the CNP of S1 is C1, CNP of S2 is C2, and the distance between S1 and S2 is minimized. So here, the distance is very general, and it could be the tandem duplication distance, right? But unfortunately, for this, distances, we cannot make much progress so far. So basically, for breakpoint distance or stream breakpoint distance, we show that the problem is polynomial solvable. So in this case, we notice that the CNPs C1 and C2 they must be different, right? Otherwise, the solution is trivial. So here is a definition for string breakpoints. So basically, you try to match two substrings with between A and B. So AI plus 1 forms a match with BJ plus 1 in B. If there's two sets AI plus 1, BJ J plus 1 are equal. In graph theory, I mean basically if you form a bipartite graph H whose vertices are two substrings in A and B respectively, basically in this case there's an edge between AI plus 1 and BJ plus 1. So for the breakpoint distance, well, we first compute a maximum matching in H. The matched two substrings form adjacency, and the unmatched ones form breakpoint. Here is an example. So CB would match with this BC. You would have three matched pairs, giving us three adjacencies BC, BC, CD, and the remaining ones they are all breakpoints. You have basically a total of 6, right? So remember that the number of adjacencies and breakpoints, so they are complementary to each other. So you can show that in fact the breakpoint distance is the length of A plus the length of B, I believe minus 2 minus twice the number of adjacencies. So in other words, if you can maximize the number of adjacencies, then you compute the corresponding breakpoint distance. They are symmetric. So this concept of breakpoint distance was first proposed by Engelbart et al. 13 years ago, which generalized traditional breakpoint concept on permutations. Notice that for this new kind of breakpoint and definition. So even if there's no breakpoint in A and B, that does not mean A equals to B, or A equals to B's reversal. For instance, you can verify that if A is 1 2 3 4 1 4, B is 4 1 2 3 4 1. There's no breakpoint in A and B, but certainly they are not equal, right? And even if you reverse B, it is still not equal to A. Okay. Nonetheless, when the length of AB are longer, the few breakpoints implies the more common adjacencies, and certainly the more similarity between A and B. Okay. So in our algorithm, we just try to maximize the number of adjacencies. So before presenting the algorithm, two more concepts. So given an integer vector in n dimension, u1, u2, un, SU is the multi-set of letters corresponding to U. So if sigma is A, B, C, D, E, U is 3, 2, 1, 0, 1. So SU is A, B, B, C, E. Okay. So little s for let Z be a multi-set of letters. Little s of Z is a string where each letter in Z appears exactly once. Certainly, you should count multiplicity in this case. So, for example, with respect to this U, the corresponding or this SU. So this SSU or SU is simply AAA BBC. Okay, and remember that here this SU or SU is not unique. Certainly, you can take any permutation of this, and we will make use of this property. Maximum common subvector, W is obtained as follows. You take the first component of U and of V, and among 3 and 2, you take the minimum. For the second one is 2 and 1, right? Again, you take the minimum, you get 1, etc. You get this W. So this is an alternative in the definition for maximum common subvector. So over here, we have, finally, the algorithm. To save, time, I will just run over, this example. Sigma is of size 5, A, B, C, D, E. C1 is 2, 2, 2, 4, 1, and C2 is 4, 4, 1, 1, 1. Okay. So we first of all we compute the maximum common subvector V of C1 and C2. So V in this case is 2, 2, 1, 1, 1. Okay. So this set SV is simply 2 A's, 2 B's, CDE, right? So SC1 is AA, BB, CC, D, 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 E. Okay, and SC2 is 4 A's, 4 B's, and CDE. Okay. The most important thing about this algorithm is that first I compute the symmetric difference, the difference. The difference, in of these two sets, SC1 and SC2. So X is SC1 minus SC2, so we have C, D, D, D. And Y is SC2 minus SC1, which is A, B, B. Okay. So the important thing here is that I want to find X, Y satisfying this condition. So X is not equal to Y. But X, Y, are both in this set SV, and exactly one of them is in X, and the other is in Y. So in this case, we select a little x as D and A. So they are both in SV, and one of them, D, is in X, A is in Y, right? So as you will see, this is, X and Y is computed to help us to generate one extra adjacency. Okay. So last, a couple of steps. So we first compute, S, little SV, which starts with X and ends with, Y, using, well, this, SV, right? So it's basically, D, A, B, B, C, E, A. Okay. So then, I will add, D from X at the end of, this little SV to obtain little S1. And for, little S2, I will add, A from Y at the beginning to obtain basically this common adjacent AD and AD over here. So for the remaining ones, you just put them arbitrarily at one of the ends of S1 and S2. So in this case, basically, I put the remaining ones in X, which is CDD, on the right, of little S1 to obtain capital S1. For S2, I do the same. I put the remaining elements in Y minus A, which is ABB. I put it in on the right. So this is very much, the algorithm. So in some cases, you will see that, it might be not possible, to find, this X, Y satisfying this condition. So in that case, the number of adjacencies would be one less. Okay. So this is a theorem. Let the C1, C2 be polynomially bounded, meaning, if you sum the corresponding elements, it gives you, a polynomial of, n. So the number of, common adjacencies generated by the algorithm is optimal with a value either n star or n star minus 1, where n star is the summation of all the elements in the common, well, the maximum common, subvector, V of C1 and C2. Okay, and as I just said, before, the reason why we could have, the optimal solution value or optimal number of, common adjacencies being n star or n star minus 1 is based on whether this xy exists. Okay. Lastly, if we just want, return, the number of common adjacencies, then, the polynomially bounded condition can be withdrawn because we can work directly, on, the CNPs, I believe. Open problems. First of all, for the MCNG problem, when S is a permutation, when S is a permutation, or G is a permutation, we don't know whether the problem is NP complete. Okay. And secondly, for the copy number profile conforming problem, we don't know whether the problem is solvable using any of the other distances except the breakpoint distance. Okay. For example, tandem duplication distance. Okay. This last one, I put it in yellow. This is a question related to duplications and deletions on strings, but they have nothing to do with something I have covered for today. So in this case, I want to convert S to T over the same alphabet using the minimum number of tandem. Segmental duplications and deletions. Remember that in this case, it is always possible. It is always possible to convert S to T. Okay, but if we want to minimize the number of operations, in this case duplications and deletions, then we don't know the complexity. Okay. Okay, so this concludes my talk. It's a little bit hectic because we are doing this online, and the materials I'm presenting is so long. But hopefully, we can discuss some details during the online session. Thank you.